Leah.
Here.
Thank you. Today we're going to be kind of going back and forth between this and the book, but also back and forth between chapter 2 and chapter 6. Okay. If we look at the very beginning of section 2.2, as predicted, the warm-up is a little bit obtuse. Give an example of a sport. In the class of sports. What's the difference between an example of something and a class of something? I have no idea what the hell they're meaning by that, so we'll just skip the warm-up. Humans seem to have an insatiable desire to make sense of everything around us, often by classifying things, putting them into boxes, categories. Labels. Probably the best example of that effort is that thing, which we're going to be talking about today, and in much more detail later on in the year. But we draw some sort of peace and comfort from making sense out of stuff. And you guys do it all the time, even unconsciously. Even when you're arranging your stuff for study. What do I have to focus on most? What's the hardest stuff? What's the easiest stuff? How am I going to study for multiple choice? How am I going to study for written response? These are the types of questions I need to look at in detail, that type of thing. We currently classify everything in the physical world as either a form of energy or a form of matter. That's true. There's only two things in the universe, matter and energy, but you learn at the very end of Science 10, most of this we can't see, or at least we think most of what is out there that we can't see is matter. There's gravitational effects, phenomena that we can't explain unless we say that there's a whole bunch of form of matter out there that we can't account for. You can't see it, so it's dark. There's even suggestions that there's dark energy, which basically is an admission that there's a whole heck of a lot of about this we don't know. But that's a good way to start categorizing stuff. What's in the universe, matter or energy? Because chemists deal with matter, we're going to start with that. This matter map is not intended to be something that you memorize. I'm not going to say, draw the matter map. But what we will go into is, what's the difference between a pure substance and a mixture? What differences? What's the difference between maybe a metal and a metalloid? What's the difference between a solution and a colloid? That type of thing. But not here, draw the matter map, 10 marks. I'm not going to do that. All right? This division of one category into a pair of others is something that's often done in biology when we classify organisms. How many of you are in life sciences living? Have you talked at all about classification? Kingdom, phylum, class, order, family, genus, species, any of that? Okay, well that's kind of what I'm talking about. That's how we classify life. And in that classification scheme, there's also often one category that we divide into two. And then each of those categories we divide into two. That's called a dichotomous key. And we do that several times in this matter map. So matter, we divide it into two things. Pure substances and mixtures. We divide the pure substances into two things. Mixtures, we divide them into two things. We divide each of those things into two things. Some of the things we divide into three, but the idea of a category becoming a subcategory, becoming a subcategory beneath that is often the most logical way for us to make sense out of the world around us. I like this matter map for a couple reasons. Number one, it has the salient features of each in bullet form right under the category. It's also the whole thing on one page. Gary does it kind of in piecemeal. The difference between this and what he's done is also that it's on opposite sides. So he puts the pure substances on the left, the mixture on the right, this is the other way around. Maybe what you want to do is put the word pure over substance. Might make it easier to distinguish between a pure substance and a mixture. Notice right at the top, matter occupies space, has mass. I would have added a third one there, possesses inertia. We talked about that, I think, last class. Gary gives us a little table here of pure substances, mixtures, elements, and compounds in the context of operational definition, which is what we see or what we can measure, observe, conceptual, why we see it or observe it. I kind of like what's on here a little better. So for pure substances, notice what's in bold print. One type of chemical unit, atom or molecule, chemically combined. So if it's not an element or an atom, then it's a molecule. And that unit, if it's a molecule, has components that are bonded chemically. Now Gary gets to that over here. I'm going to forget about this bullet. I don't know that I would have put that in there. Okay? Because there is one type of chemical unit, the proportions of a pure substance are fixed. So for example, water. Water is a pure substance. It's a molecule. The components of water are hydrogen and oxygen. For every 18 grams of water, you always have 2 grams of hydrogen, 16 grams of oxygen. Because the components are chemically combined, the proportions are fixed. In other words, we never change the amount of hydrogen relative to oxygen. And if the proportions are fixed and constant, so are the properties. The properties of water are always the same because the components of water are always the same. And the relative amounts of the elements in that are always the same, all because they're chemically combined. I can't change the amount of hydrogen relative to oxygen. Characteristic of a pure substance. So it says here, same proportions, fixed proportions. One set of properties, fixed properties. There's a name that chemists give to this, the same proportion thing. It's the law of constant composition. In other words, if it's a pure substance and the components are chemically combined, fixed proportions are always there, which means fixed properties. As opposed to a mixture. Now notice what is in bold print on the mixture side of that matter map. 2 or more substances physically combined. No chemical bonds. And if they're physically combined, then I can change the relative amounts of each. And that's why it says random proportions. Great example, sodium chloride's a pure substance. We've got as many sodium ions as chloride ions, always. Water's a pure substance. Same number of hydrogen atoms relative to oxygen, always. But when I mix the salt into the water, now I have a mixture. And I can change the amount of salt I put into the water because it's a mixture. I can put a little salt in water, or I can put a lot of salt in the water. Because I can change the amounts, I can change the properties. If I add a little salt to water, what are the things that are going to change? Well, the density of that liquid is not going to be the same. Because something in there isn't water. Conductivity is going to change. Conductivity is a result of mobile ions. If I add a whole bunch of ions, the conductivity will be higher than if I add only a few ions. Boiling point is going to change. Melting point is going to change. All of those properties will change because I can change the amount of those components. And because they're not chemically combined, the relative amounts of each can be varied. Which means random properties due to random proportions. I can vary the amount of each. Okay? And if the components of a mixture are physically combined, then I should be able to separate them physically. And that's really what section 2.3 is about. We're going to talk about separation techniques. I'm not going to follow the book that closely, but we're going to go through 7 or 8 separation techniques. And they're all going to be physical. And if they're physical combinations, then they should lend themselves well to physical separation techniques that are based on different physical properties of the components. And that'll lead us eventually at the end of the section into our first lab, titled appropriately, Separation of a Mixture by, and the technique we're going to use is chromatography. Okay? All of the techniques are going to be based on different physical properties. If we travel down the mixture side, we get to things we're going to talk about next class, homogeneous mixtures and heterogeneous mixtures. We can further divide each of them into 2 categories, solutions and colloids down the left, suspensions and mechanical mixtures down the right. But we'll get into those next class. I want to travel down the right-hand side. So as we go down to element and compound. So, 2 types of pure substances. An element, one kind of atom, cannot be decomposed into other substances. The very first definition of the element after earth, air, fire, and water nonsense was courtesy of Robert Boyle. In his book, you guys remember the title of the book? Skeptical Chemist. His definition of element was brilliantly succinct, an unmingled body. That's exactly what that is. It's only got one thing in it, unmingled, not made of anything more than one thing. About 100 years later, a French chemist named Antoine Lavoisier gave us maybe a little better definition. An element's the final form that can be reached by the chemical breakdown of matter. But it kind of means the same thing as Robert Boyle. So when Boyle said that in the late 1600s, an unmingled body, he was kind of giving scientists a roadmap. If there's only one thing in it, then maybe it can't be decomposed into anything else. Same with Lavoisier, the final form that can be reached by the chemical breakdown of matter. In other words, if you run out of things you know to use to try to separate stuff, and you can't anymore, maybe what's sitting there is an element. And with that definition, basically society was given a recipe for discovering elements. And in the 1800s, a whole bunch were discovered. And we're going to talk about how those things are arranged in a few minutes. On the other hand, we have compound. More than one type of atom chemically combined. Fixed proportions, fixed properties. It can be decomposed, but only with chemical reactions. Okay? If we go down the element side and further divide that, then we start to get into the periodic table. So, the biggest division in the periodic table are these 3. I'm going to flip ahead to chapter 6 in a minute. But that thing, depending on your frame of reference, there are learned people in society that consider that, next to the Bible, the most important document humankind have ever produced. And if you're not religious, the most important document. That makes sense out of all the elements in the universe. And the amount of data, the amount of theory, the amount of research that had gone into that thing is staggering. And anybody that does chemistry for a living has one of those within eyesight. And if you knew all of the information in the periodic table, you could teach chemistry at any level, anywhere on the planet. There are professors that spend their careers doing research on the relationships that fall out of how those elements are arranged in that table. And I think I've asked this question before, but what does the first word mean?
Periodic means like they're arranged in a certain way.
You can be more specific than that, you're right. But what does the word periodic mean? How many of you guys are in physics? Have you talked about periodic motion yet, like the motion of a pendulum? Okay, you will. But that's maybe a clue to what the word means. Periodic means regularly repeating. So for example, when a pendulum swings through its arc, the exact amount of time always taken for that motion to occur. That word is courtesy of a law that a Russian born in the forests of Siberia in the late 1860s formulated. The guy's name was Dmitri Mendeleev. And after Dalton's atomic theory at the beginning of the 1800s, about 1808, so Dalton returned society, all matters made up of atoms. And then coupled with some of the research of other scientists and Lavoisier's definition, between 1808 and about 1868 or 1869, also with the help of the electric battery invented by Alessandro Volta, a whole bunch of elements were discovered. And a number of chemists, another number of scientists tried to make sense out of, arrange the elements in a meaningful way. And Mendeleev was the most successful for a couple of reasons. And when we get to chapter 6, we'll go into some of those reasons. But what Mendeleev did is he took little filing cards, like what you might have, say, in a speech contest. And he wrote everything about every element that was known on an individual filing card. Its mass, it's the formula of its oxides, formula of its hydrogens, specific heat, density, melting point, boiling point, all of that. And then he arranged them on a bulletin board. He tacked them up in order of increasing atomic mass. And he discovered something. He found that at regular intervals, say the first one here, 8 elements later, another element had properties similar to this one. Not identical, but very similar. Then the next one, the same interval, another element had properties similar to that one. And it happened over and over and over again. So he knew he was onto something. And what he did is he took the elements that had those similar properties and he put them underneath each other. And thus began the first periodic table. The law that he discovered is the answer to the question, what does the word periodic in the term periodic table mean? Excuse me. And not to shamelessly plug the stuff I wrote, but on the top of page 283, there's the first, there's Mendeleev's periodic law. Proposed to the Russian Chemical Society in March of 1869. If elements are arranged in order of increasing atomic mass, a pattern can be seen in which similar properties recur on a regular periodic basis. So what repeats at regular intervals? Similar properties. Now, in 1869, we were still almost 30 years away from the electron being discovered. So Mendeleev knew nothing about electrons, protons, nuclei, none of that. As far as Mendeleev was concerned, an atom was a tiny little indivisible sphere, courtesy of John Dalton in 1808. So Mendeleev had no idea why these similar properties kept repeating. And that's why it's called a law, not a theory. Laws summarize regularities, phenomena, but they don't offer an explanation. Theories do that. And about 40 years after the periodic law, the why behind the what in the law was worked out through the details of something called quantum mechanics. And quantum mechanics, married to the periodic law, are arguably the best example of theory and laboratory data that's ever been accomplished in the realm of human history. Okay? And when the details of quantum mechanics were worked out around the end of the 1920s, early 1930s, and the periodic table was looked at, they matched perfectly. But the periodic table was essentially in place in its modern form before the why was ever discovered. And the more we discovered about the why, the more the periodic table made sense. And hopefully you guys will get to that realization probably around February. Okay? Let's talk about the three main divisions then. Metal, metalloid, and non-metal. And by the way, if you're interested in Mendelev's, one of his first versions of his periodic table, page 283, middle of the page. Now that, at first glance, that looks nothing like that. Okay, because there's only about 65 or 66 elements known. Now there's 118. But if you look closely, you can see some similarities. So let's look at the column top left. You see it says Grupo 1. That's Russian for group. You see underneath that, it's got this symbol. See that? So this is just a generic letter for an element. This is back in 1869. That's how we used to write this. Okay, that's how the formulas used to be written. So what was Mendeleev saying in that group? He's saying all of the elements in that group have that formula for their oxide. Okay. Now, again, it doesn't look like that thing, but look at the elements in that first group. Lithium, potassium, sodium, rubidium, cesium, lithium, sodium, potassium, rubidium, cesium. Now, there's a few others in there that at first glance shouldn't belong there. Notice he's also got copper, he's also got silver, and he's also got gold. Copper, silver, and gold are among the three least reactive metals in the table. So it seems weird to put them in the same family with the most reactive metals in the table. But the reason he did it was because of the formula of their oxides. Silver, copper, and gold can all form oxides with that ratio, which is a clue to what Mendeleev considered a priority. He looked at chemical properties. Sometimes elements were in the same family that shouldn't based on how they looked, but went there because of their properties, their chemical properties. Okay? We're going to spend a whole lot more time on this, but just before we leave it, if you look through that table again, there's several places where he's got blanks. And elements 44, 68, and 72. All that means is, in that table, there should be an element that goes there, but there wasn't. In other words, he said when an element's discovered with this mass, it should go right here. He didn't try to fit stuff into where it should go based on its mass. He let the properties dictate. So he knew that there were going to be elements that were going to be discovered with those masses. And based on where the blank spaces were in his table, he said when they are discovered, based on what else is in those families, these are the properties it should have. Now, when predictions like that are made, and then years later they play out to actually be true, that's when science goes, you're onto something. Great example of how specific and correct his predictions were. If you flip the page. In 1871, he predicted an element would be discovered. That was one of the blank spaces. Mass of 72. Density 5.5 grams per cubic centimeter. Specific heat 0.31 joules per gram per degree Celsius. We learned about specific heat last year. Oxide formula 1 to 2. Oxide density 4.7 grams per cubic centimeter. Chloride formula 1 to 4. 15 years later, an element was discovered with a mass of 72.3, density 5.47 grams per cubic centimeter, really high melting point, specific heat exactly what he had predicted, oxide formula as he had predicted, oxide density exactly what he had predicted, and a chloride formula 1 to 4. That's germanium. Now that's not the only example. His other predictions were borne out too. That means whatever he was onto had some sort of credibility. But he had no idea why. He had no idea why these properties that were similar kept repeating, because he had no knowledge about atomic structure. And again, that's why we call it a law, not a theory. The modern periodic table is given on the bottom of page 285. The modern periodic table, which is what you see in the wall here, was only in its complete form as of 2017. Prior to 2017, there were 3 or 4 synthetic elements down here that IUPAC, which is kind of the UN of chemistry, the International Union for Applied Chemistry, hadn't decided yet who really had synthesized these things. They didn't discover them, they made them. The biggest naturally occurring element is uranium. Anything bigger than uranium doesn't exist naturally in the universe. And that's why these elements all pass uranium are green. And then you go, wait a minute, that's green, and it's between 2 stable elements. That's green, and it's between 2 stable elements. All that means is that these probably existed at some point, but they were too unstable, too radioactive to remain, so they decayed away a long time ago. Technetium was the first synthetic element made. And it's, if you go into nuclear chemistry, you learn about sort of numbers, protons to neutrons, that are particularly stable, but also particularly unstable. So we believe that when the Earth was formed, there was probably technetium there, but it long ago decayed. But it was the first one we made, in a particle accelerator. Basically, we fire protons in a nuclei, and as soon as one sticks, we get another one. It's just really radioactive, okay? And that's what that thing is. Down here, there's another one, promethium. We didn't really make that one on purpose. That one was discovered at the remnants of the first atomic detonation at Ground Zero at Los Alamos. An element, evidence of an element that chemists had never seen before. And quite appropriately, they named it after the Greek god of fire, Prometheus, so they called it Promethium. That's the first time they found it. But these never existed. And a lot of them are named after either where they were discovered, who discovered them, or after some famous chemists or famous researchers. So some names you might recognize. Rutherfordium, Ernest Rutherford. Bohrium, Niels Bohr. Meitnerium, maybe not. That's named after Lise Meitner. She was a German researcher that worked in Berlin with another German researcher named Otto Hahn. Lise Meitner was the one that actually figured out what was going on when a nucleus was split. In other words, what was going on with fission. And unfortunately for her, and the time where she lived and where she lived, she was Jewish. So they were doing their research almost at the outbreak of World War II, when Hitler came to power. So Lise Meitner basically had to leave and go into exile, or she would have been sent to a concentration camp. But she was the one that figured out what was going on. Otto Hahn got the Nobel Prize for it. And so the Nobel Committee kind of screwed that up. They should have given her credit, which they didn't. And that's why years later that element was named after her, in honor of Lise Meitner. Okay? She really figured out what was going on when nuclear decay and nuclear fission occurred. Not Hahn. He worked with her, but she figured it out. Anyway, I digress. So these things, notice they all have that little symbol. And up here it says synthetic, human made. Some of these things are around for only fractions of a second, they're so unstable. But they've been around, they're around long enough that some of their properties, in some cases, can be articulated. You're never gonna have to memorize that thing, okay? And if you look at all of the elements in the table, the three biggest distinctions we make are these: metal, metalloid, non-metal. If you look at Gary's periodic table, or chunk of it, at the bottom of that page, you'll notice these little pink or purplish shades through these 8 elements. He's representing that as the metalloids. This is not a metalloid. Astatine is a halogen, it's not a metalloid, but the other 7 are. So we're going to talk about what distinguishes a metal from a non-metal from a metalloid, which is why we're in this section. So if you flip to the top of page 286, turn the page. Consider the periodic table in figure 612, that's the bottom of the previous page. The first distinction among the elements relating to their properties that we'll discuss is their classification as metals, non-metal, or metalloids. The staircase line, you don't need to know what it's called, but it's called the line of Amphoteric, so that's this thing. Distinguishes metals on the left from non-metals on the right. So the first thing you notice is most of the elements are metals. Okay? Everything to the right of the line are non-metals, everything to the left are metals. And there are 7 elements along that zigzag line that refer to as metalloids, semimetals, or semiconductors. But what distinguishes a metal as a metal? Probably if I asked you for what are the properties of metals, you could probably all suggest something. So this is a metal. What might be the property of that? Even if you're not looking at this deformed paperclip. Any idea what properties we assign to metals?
Can you conduct electricity?
Conduct heat and electricity, yeah. Do you know what happens when electricity is conducted? Do you know what that means? What will a conductor allow to have happen inside? What does it mean to conduct electricity? What's being conducted? What's moving?
Electricity moves through it.
What is electricity? What's moving? Electrons. Yeah. So for some reason, metals let electrons move through them quite readily, which is kind of weird when you think of it. Because metal atoms, as is the case with all chemical bonding, has to do with electrons. And yet, if they let electrons move through them easily, then what type of bonding must that accommodate? Think of this wire, if you will, as a garden hose full of water. And if I put water in one end of a garden hose full of water, water's going to come out the other end, right? And as long as the water's on in this end, the water's going to keep flowing. That's what's going on here. When this conducts electricity, the electrons are moving through it, which is a specific type of bonding that isn't ionic or covalent. It's called metallic bonding. And on this sheet, it's way over here in the bottom right. Now, it's not really part of the curriculum to talk about metallic bonding, but I'll just give you a kind of a nutshell overview. Think of the atoms in a metal think of the nuclei, the positive part of the atom being the rocks on a riverbed. And think of the electrons as being the water over those rocks. So metal atoms don't hold on to their electrons that tight. The electrons bond the atoms together, but chemists will speak of things called free electrons. So electrons can move through metals, even though the metal atoms are all stuck together. the electrons associated with those nuclei are not held in place. They can move. So when electrons are being conducted through a wire, the electrons that are moving through aren't the electrons, they're not stuck between the nuclei, bonding the atoms together like they would be in sodium chloride or a covalent compound. The electrons are involved in bonding, but they're not held tightly by an individual atom. And that mobility of electrons is really the cause of a whole bunch of physical properties. The fact that metals don't hold on to their electrons tightly is also why I can take a metal wire and I can bend it. Now, what am I doing when I bend it? Well, I'm changing bond angles. I couldn't do that if the electrons holding the atoms together were held tightly. I couldn't bend it. I couldn't hammer it into sheets. We call that property malleable. If I take a piece of gold the size of a matchbox, I can hammer it into a sheet big enough to lay it over a tennis court. And every time I smack it with a mallet, malleable, I don't break chemical bonds. I just change the shape of what I'm hitting. The fact that the electrons aren't held tightly is why I can take a metal and stretch it into a wire. That's called ductility. It's why it's bendable. It's why it conducts electricity. Another property of metals, maybe the first property to mention, is they're all solids at room temperature, except for mercury. There's only two liquids in the table. One of them is mercury, a metal. One of them is bromine and non-metal. Metals are all shiny or lustrous when freshly cut or polished. Now I have to add that proviso with that freshly cut or polished because these are all soft enough to be cut with a knife. But they're so reactive that as soon as I cut them, that shine disappears almost instantly. And the farther I go down in that family, the faster the shine disappears, the more reactive they become. So if you look at the bullets on the top of page 286, those 7 bullets for metals, the 3rd, 4th, 5th, and 6th are all a result of the fact that metal atoms don't hold on to their electrons tightly. The last bullet, though, isn't a physical property. The last bullet is a chemical property. But it also results from the fact that metals don't hold on to their electrons. During chemical changes, metals tend to give up electrons relatively easily to form cations. If they held their electrons tightly, they wouldn't do that. And chemically, that's all they ever do. They never take electrons. They never form a metal negative ion. Metals happily give their electrons away. So 6 of those bullets are physical properties. The last one's a chemical property. What about the nonmetals? There's far fewer nonmetals than there are metals. They're in the upper right-hand corner. Usually gases or brittle solids at room temperature. And if they're brittle solids, when you hit them with a mallet, they crumble. Which probably means they're holding onto their electrons pretty tightly. You can't change the bond angles. They're not ductile, they're not malleable, they're also not conductive. Which is again suggestive of the fact that they're holding onto their electrons pretty tightly if they don't allow electrons to move through. Solid nonmetals ranging in appearance from dull or lustrous to translucent to opaque. So not nearly the same regularity with appearance as the metals. And one family of nonmetals, the halogens, is the only family in the table where all 3 states of matter are represented. Top 2 are gases, that's kind of a yellowish green gas. That's a green gas, that's a dark brown liquid. That's a dark purple solid, and that's a black solid. It's radioactive. And there's maybe only an ounce of that in the entire planet. So most chemists have never seen astatine, but it's a halogen. Okay? Poor conduction of heat and electricity, and once again, the last bullet there is a chemical property. During chemical changes, tending to gain electrons from metals to form anions, or share electrons with other nonmetals. So it seems that nonmetals, rather than wanting to give electrons away, somehow want more, either through sharing or taking. Now what about the metalloids? Well, along the staircase line are several metalloids, also called semimetals, also called semiconductors, including the elements boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. No astatine. Now, we call them metalloids, meaning they're metal-like. Well, what's similar about these elements to metals? Well, they're all solids, and they are conductors. But why we don't just call them metals is how their conductivity varies with temperature. So with a metal, the conductivity varies inversely with temperature. With a metal, the hotter it gets, the lousier a conductor is. So as the temperature goes up, the conductivity goes down. And as the temperature goes down, the conductivity of metal goes up. That's opposite to metalloids. Metalloids are conductors. But the hotter they get, the better they conduct. And the colder they get, the worse they conduct, which is opposite to metals. What's the most famous metalloid on the planet? Silicon. You guys heard of Silicon Valley, just outside of San Jose in California? Where they make silicon chips and all other things related to computer technology. One of the biggest companies down there is called NSC, National Semiconductor. So were it not for silicon and the semiconductor properties of silicon, there would be no such thing as the computer industry. But this astatine, that is not a metalloid. That is a flat-out, straight-up halogen, all right? We can further something like these. Remember, we're more happy when we categorize rather than not. So we can take metals and divide them into a whole bunch of families. And that's what Gary means by et cetera here. These are the only two really which we have on metals, which we have names for. The other families are usually just numbers. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 vertical columns, or 18 vertical columns. Some of them have names. So alkali metals are group 1, alkaline earth are group 2, halogens are group 17, noble gases are group 18. I would have preferred that if you're going to put the et cetera here, you would have put it over here. If you look on the back of your book, this cover, the families are numbered, okay? Now notice at first glance what's obviously different between this and that. What do you notice that's here that isn't there?
The space.
They're split into 4 groups, aren't they? And there's a reason for doing that. And that grouping, although it looks a little weird here, is going to come in really handy when we start talking about quantum mechanics. But notice the group numbers are across the top, 1 through 18. And notice we also number the horizontal rows, the periods, 1 through 7. Okay? We're not going to go into these in the detail we do in chapter 6, but alkali metals, far left, the most reactive metals in the table. They only ever do one thing. They give 1 electron away. The number of electrons they have in a neutral state is the same number of protons, which is this big red number. And that number, by the way, is always the most prominent in an element space. Because the definition of an element is its atomic number. Any nucleus with 19 protons is potassium. Doesn't matter how many neutrons are here, doesn't matter how many electrons, it's potassium. So that defines an element. For a neutral atom, it also tells us the number of electrons. These are the most reactive metals in the table. That's one of their chemical properties is similar. What changes as we go down is how big they get. And as they get bigger, they get more reactive. And if you think about it, it makes sense, because the only thing they ever do is give away one electron. 100% of the time. In all of their chemical behavior, they form 1+ cations. And as the atoms get bigger and bigger, it's easier for that one electron to be given away because it's so far from the nucleus. All of them are soft enough to be cut with a knife. All of them react violently with water, more violently as we go down. And there's a whole bunch of other problems. Next to the alkali metals are the alkaline earth metals. Alkali and alkaline refer to basic substances. So why do we use those terms for these? Well, if you take these oxides and throw them in water, the solution gets basic. Same reason. These things are almost as reactive as the alkali metal, but not quite. The only thing they ever do is give 2 electrons. So they always form 2+ cations. Not as easy to give away 2 electrons, because after you take the first electron away, what you're left with is a 1+ charge. So it's not as easy to take another negative charge away from something that's already positive, but they're still pretty reactive. These things in the middle, these are called the transition metals, and we'll talk a lot more about transition metals when we get to chapter 6. But they're still metals. Over here, when we get to the tall blocks again, we get into elements that may be a little more familiar to you. This family, the halogens, are not only the most reactive non-metals, they're the most reactive elements. And with these, reactivity increases bottom to top. Again, which makes sense when you look at what's happening when they react. They all grab one electron. They don't give anything away, they grab, as is consistent with being a non-metal. And they do it violently. So if these are the most reactive elements, and reactivity increases bottom to top, that makes this the most reactive element in the table, which it is fluorine. If something doesn't react with fluorine, it doesn't react with anything. Then we get to the noble gases, unreactive. 1 electron away from the most reactive elements in the table, we have a family of gases that in nature never react with anything, which suggests reactivity and unreactivity. We don't study noble gases because they take part in chemistry. We study them precisely because they don't. What about them makes them so happy? Just like nobility never mixes with common folk, noble gases don't mix with anything else because they don't need it. They don't need anything from anything else. They're quite happy. And the closer a family is to being like a noble gas, the more reactive it is. Halogens, noble gases, alkaline earth, alkaline metals. Normally the other families are just given numbers. Why do you think alkaline metals are the most reactive metals? And halogens are the most reactive non-metals / elements? Why would it be in their best interest? Why are they so reactive?
They're only one away from making
Only one what?
um,
Electron, precisely. That's why. The closer an element's electron number is to being like a noble gas, the more reactive they are. And we can say more than just tendency to react. We can talk about charge. So write this down. It may be obvious based on our conversation, but title this Predicting Ion Charge from Position in the Periodic Table. Predicting ion charge from position in the periodic table. Except where large ionic charges result, and then in brackets write this. Except where large ionic charges result greater than plus or minus 3. Except where large ionic charges result greater than plus or minus 3. Atoms of the elements atoms of the elements make sure you're writing with the hand you normally write with. It saves time. Atoms of the elements will tend to give up or gain, except where large ionic charges result greater than plus or minus 3. Atoms of the elements will tend to give up or gain as many electrons as are necessary, as many electrons as are necessary to acquire ACQUIRE, to acquire the electron configuration, which is just fancy speak for same number of electrons as, to acquire the electron configuration of the, then underline these last three words, nearest noble gas, except where large ionic charges result, greater than plus or minus 3. Atoms of the elements will tend to give up or gain as many electrons as are necessary to acquire the electron configuration of the nearest noble gas. Now that doesn't work for every element, but it works for elements within 3 of the noble gases. If you look in the back side of the second last page in your book, you see this table here, right? By the way, you'll always get this from now on any test, in the same way that you'll always get this periodically. The positive ions are on the top, the negative ions are on the bottom, listed alphabetically by name, not symbol, okay? So let's see if we can make sense out of what you guys just wrote by looking at some examples. I'm going to look at these elements. So these are the charges of the stable ions. And notice I put the number in front of the charge. It's not +3, it's 3 plus. Is there ever a case where the charge goes in front of the number? Yeah, but that's when what you're referring to is what's called an oxidation state. That's Chem 12. Okay? So, how many electrons do each of those ions own? Well, aluminum's atomic number is 13, which means as an atom, it's got 13 electrons. If its stable ion is 3 plus, that must mean it's given away 3, correct? Then why would it want to give away 3? By the way, that's all it ever does. Well, look at this. 1, 2, 3. Look at magnesium. How many electrons does magnesium own? What's its atomic number? 12. If the only ion it ever forms is 2 plus, if it gives 2 of those 12 away, it has how many? 10. If you count the electrons for any one of these ions, all of them have 10 electrons, which is the same number of electrons as 1. Now, are there things with ion charges as big as 4 plus? Yes, there are. Same with anions. But as the number of electrons gets too far away from the noble gases, it's hard. 4 plus cations are difficult because you're trying to pull an electron away from something that's already got a 3 plus charge, and that's difficult. But if an atom is close to being like a noble gas on the outside, same number of electrons as, electron configuration, that usually dictates what ions it'll form. And notice, non-metals, they gain electrons. Metals, give them away. That's the end in sight. That's what they're trying to be like. Now, you've heard noble gases are stable. we're gonna go into a lot more detail. What is stable about it? Why do all the noble gases say 1? Why do they always have 8 electrons on the outside? What's the stability associated with that magic 8 number? And there's even a rule called the octet rule, all right? Now, that doesn't work for a lot of elements. So, for example, if you look at that table of ions, what's the charge on silver? 100% of the time. It's on the top under S's. What is it? Look at your table of ions. Top half. What's silver? Always. 1 plus. How does that make sense? Take 1 electron away, it's got the same as palladium. That doesn't make any sense. What about iron? 2 plus, or even more commonly, 3 plus. But again, how does that get us anywhere near either of these? Copper. 1 plus and 2 plus. What is going on there? So it doesn't work as well for these, or even zinc. Zinc always 2 plus, 100% of the time. In what best interest would zinc have in losing 2 electrons? And yet that's all it ever does. Gallium, you might think, okay, that's weird. What's the charge in gallium? Is it on the table? It would be under G for a cation. Nope, not a common ion. Guess what its charge is? What is it underneath?
3.
What element is gallium underneath?
3 plus.
Aluminum. What's aluminum's charge?
13.
So is gallium's. And yet you can't look at that and go, oh, I see why it's going to lose 3. Therein lies some of the challenge. The clue is it's got to do a whole lot with valence electrons. And gallium has 3 valence electrons, just like a group. Even though you can't necessarily tell based on where it is. I don't expect you to solve that mystery here. But by January-ish, once we've talked about the details of quantum mechanics, you'll be able to look at that table and go, yeah, I see why iron 3 plus is more stable than 2 plus. And I see why zinc's always going to be 2 plus. And I see why silver's always going to be 1 plus. It'll make perfect sense. But you can't use that. You can't use that nearest noble gas thing. Stability is achieved another way. Okay? Now, I could go into much more detail on the periodic table. I don't want to just yet, and it would be unfair of me to try to do it because you guys haven't learned about quantum mechanics. But a lot of students wonder about this. Why is this down here? This is kind of the short form of the table. If you look at these numbers, you see where it says lanthanum 57 to 71? If you take this and go way over, plunk this in here. So after lanthanum, put all of these. Then after lutetium, number 72. Separate it after actinium, put thorium. And after valerium, another 40. That's the long version of the table. And if you flip the page to top of page 290, that's the long form of the periodic table. That's where there's 2 things that we took out go. And if you look, the little symbols over each of those boxes, you see S, F, D, and P. Those are things we refer to as orbitals. And that's quantum mechanics. Okay? Back in Science 10, or not just Science 10, Science 8, Science 9, you guys talked about Bohr models, right? Remember where the electrons were in their orbits? Nice little concentric circles following the circular path around the nucleus. There's no evidence to suggest that they ever did do that. Electrons aren't like that. They're actually worthy of more regard than that. So by January or February, you guys will have abandoned the word electron orbit. There is no such thing. You will have, on the other hand, happily embraced the term electron orbital, which isn't an orbit. It's not a path. So electrons do not orbit the nucleus like planets orbit the sun. Although that analogy is kind of simplistic, but they don't do that. And the Bohr model, proposed in 1913, was abandoned not that long after, which may beg the question, then why did you guys make us learn it? Well, because it's a simplified version of what's a hell of a lot more complicated. But electrons, not only do they not follow prescribed paths around the nucleus, they're not actually negative particles either, which is weird. Yeah. Remember I said, or maybe I said, we live, we make sense, we encounter the world of big, slow things. Remember we saying that? When things get really fast, we need relativity. But when things get really tiny, we need quantum mechanics. And quantum chemistry suggests things that seem ridiculous in the world of big, slow things. And one of them that's ridiculous, or seems ridiculous, that a lot of scientists couldn't agree on, like Einstein and Bohr. What it means for electrons, what their behavior seems to suggest, contradicts what you guys have learned before. But we're going to get there, and we're going to get there around, as I said, January, February. And once we get to that, then that'll make a whole lot more sense. And we talk about quantum mechanics in chapter 5. We talk about the development of our understanding of the atom. And we talk about Dalton and Rutherford and Bohr. But you're also going to hear names like Erwin Schrödinger, Werner Heisenberg, Louis de Broglie. And those were young guys. They were in like their 20s. And yet they rewrote reality as people knew it, which I think is pretty cool.
Afternoon, staff and students. Let us prepare ourselves for grace before lunch, followed by a few announcements.
And I wrote all
In the
that
name of
stuff.
the Father, Son, and the Holy Spirit.